Hello and welcome back to another episode of Learning Rust with Git Oxide. Hello, Sydney.
Sebastian.
I hope you had a nice weekend. Mine was
I
okay.
did, yeah. It's good to hear.
Then I hope, or I think you are well rested to start with something that will probably be a little bit tricky, but maybe not. Let's see. Self-fulfilling prophecies we don't do unless everything is awesome, of course. So today is supposed to be about trait objects. So we have talked about traits already a little bit, like we had iterator, let foo be some what kind of syntax am I using here? But some iterator, this probably doesn't work at all. I just make it up. So in theory, that should give us some iterator, right? But the type here, it's not the correct type apparently. Also, that's apparently nothing you can do syntactically. Maybe this is more like it. No, it really does not like that at all, which is fair. It's kind of nonsense. Let's run this and see. Okay, so it wants to have the dyn keyword because it wants to have wants to make this a trait object. Okay. And probably all this is also not going to work. Just giving us the next error here. Specify the associated item, which is also unclear. But we can just make one up. Maybe the type inference will then kick in. Okay, down to 2 errors. Okay, so here we expected a trait object, but found an actual structure that is into iter. And when you look at what this returns, you see it returns an into iter. And this is just a structure that has all the state it needs to implement iterator. The reason you would want to do this in the first place is that you don't exactly care about the actual structure that implements an iterator. You just want the iterator itself. And you want to use the iterator trait itself and not the structure. Usually the structure doesn't give you anything extra, at least these standard library ones. They are literally just their trait that they implement, but some others might. Nonetheless, this appears to not to be working because, yeah, to make this work, I need to specify the actual type that is returned here, or do it like this. You know, why specify anything if you just if you can just infer something? Let's make it like this, just to see what type that would be. Let x be foo, and we see it's just into iter u32 as expected. So in this case, of course, you don't really care about that. But what if you have different kinds of iterators that you want to return in one function? Because then you are a bit in trouble because it's different types. How do you specify them? So let's try that. Let's remember though trait objects. These dyn iterator thingies are trait objects, and they have a bunch of properties that probably we will discover. One property we already know. You kind of can't assign that easily. This trait object, it's something special apparently. The compiler does not know its size. Without a size, the compiler can't store things on the stack either. And this is why you can't just assign this. So sized is a property at compile time that most things have, but not all of them. And if they don't have it, then it just has to be somewhere, float somewhere, and the handle that you use to access it doesn't know the size anymore of the underlying object, the size in memory. It just knows it's there and it obeys the rules of this trait. And that's a trait object. All right. Fn make iterator. Yeah, so this exclamation mark here that says it doesn't return, which you can use to say this is the end of the program. There's return is not expected here. So if you have a server running that never returns, that has to be killed or something, that runs forever, this is how you do it. I don't know. To do as always makes everything happy, so that apparently is okay because you can't panic out of that function call. But overall, you could also do this. Just have an endless loop. That's just as fine, and that just declares that explicitly to the outside. Right? That's also fine. That's just another way of writing it, which probably have just different properties as well. But you know, something we talk about another time. And this is actually useful for something. I don't know what it is useful for in most cases. It's also called the never type here, by the way, but that's all unstable, and I digress, definitely. So make an iterator. Let's just take this one here and put it up. So now we have the same problem as before. Then we have to declare the type because we want to have this into IDA, and right now we could because it's just one thing that is returned here. But what if so now we have some choice in there. So if we select one, what about this? So now we have two different kinds of iterators here. One is based on a vector, the other one is based on an array. So the storage is entirely different, the storage location, because here the storage location is on the stack, and this one is on the heap, with just, you know, a little bit of, you know, a bunch of tracking data located on the stack that can move around. Here it's the entire data structure that is moved around, but that's just on the stack. So how are you ever going to return that? Because both have an iterator of the same kind in theory, because they can both iterate over U32s.
Mm-hmm.
So I hope this is going somewhere because I did not try this before. I hope we will get this to work. That's what I mean. I think it will go somewhere, but let's see. The return type. Now we have to figure that out. The return type should be this here, array into either U32 1, because that's an array over 1 things. As we know, arrays are typed by their size. And this is why that type appears here in the array into either, which is, I think, a relatively recent addition, that this is typed by the size. It's a consternary kind of thing. It didn't even get to the point where it would have issues with this vector-based iterator. All right. So you see, these trait objects, they have good reason not to not be sized, because they don't actually, like, they actually hide the size from you, which is something you need here, because the storage location is, you know, a different one depending on what you look at. And in a way, it's also really hard to make that work, because in one case, the storage location is kind of bundled into the iterator, in case of the array, because that into IDA must then own the array so that it can move with the iterator and can move around to stay consistent, which is what into IDA usually does, right? These are consuming. So they move the thing that they iterate over into themselves so that they can keep them. And the same here, but here the actual location of the data is on the heap. Different things, hard to consolidate in a way. And there's no perfect way to consolidate this. You could say, okay, let's unify this. Let's kind of move everything to the heap. And this is where boxes come into play, finally. And there's a special way of using trait objects, which is a trait object behind a box. Because then the size is still erased, so it's unknown how big that thing is underneath, because it actually can be dependent on something at runtime here, right? That's not compile time anymore. That's, oh, it's true, so it's this size, and now it's false, so it's this size. It's not known at compile time, but it is always known at runtime, obviously, because something has to track that memory. And that's not just, you know, random. I mean, it shouldn't be. If it is, then you probably don't use Rust. So, and there we go. Now we start boxing things. And what we should box is the whole iterator. And of course we do that with both ones, so that the type, so at least both are on the heap. The whole thing should be on the heap. The whole vector already has heap allocated data, but we are interested in heap allocating the whole iterator. And these are different types, so I have to do that. So let's see. It's all red, it's all unhappy, not a pleasure right now. Same thing here. We have now a box of some very specific type.
Yes.
So it's not helping, because if we think of this, the next one here, right, this would be some box of some vector iterator. Doesn't work. Okay. So now we have to find a type that both can share. And now again, trade objects. And I can specify this here. I can say box dyn iterator of item, item being u32. And that's the syntax already. That's all. Now let's see. It actually compiles again, because the compiler implicitly made that conversion here. So that's usually quite rare to have implicit conversions of anything, to my mind. Mm-hmm. I didn't expect that, to be honest. I expected to have to write something like as box dyn iterator and then this. So that's the syntax if the type inference doesn't kick in like it does here.
And
it's a cast.
So you need the box. Why exactly? You couldn't just say you return the iterator directly with the syntax without the box around it.
You can't say that, because then the storage location of this iterator is still the stack. And it's just passed down as you return it. So the caller receives the whole bunch of bytes that are now on your stack in that function, gets moved down to where you called it. And this is either that or that, which makes it unknown at compile time. And you have to abstract over that in some way. And there are other ways. You can use an enum, right? You can use an enum with two variants. And you could say, okay, it's either that or it's that. And then you implement iterator on that enum yourself. And, you know, and always as you go next, you check, oh, what am I? Oh, I'm this. So,
okay.
But it's kind of cumbersome to do that every time, right? Like you can. And most of the time, that's what I do, to be honest. I mean, I usually use variants to have multiple different return values. Also, Git Oxide uses that. A Git object is an enumeration with multiple variants. One of them is blob, tree, tag, and commit. Yes. I should probably know that. So, and this is the way to do it if you want to keep things on the stack, but then you have some overhead because you have to implement every trait that you want to implement on this yourself. And I think there might be crates for this that can automatically do that for you to some extent for some standard traits and so on. So if you do that a lot, maybe use a crate like this. But the alternative way is to just use a trait object inside of a box. And the box
that is, oh, sorry.
That is?
Yeah, I would just as a comparison, I mean, that is also not the same as a trait guard, right? Where you say this is something that implements an iterator. It's literally something with an iterator inside the box that holds the iterator.
Yes. This is runtime now. This is all runtime stuff. This is not compile time anymore. And for all we know is behind the data stored here that is known only at runtime has or implements the iterator trait. And the dyn keyword, where there was a time when you didn't have to write that looked a bit funny because it's a bit ambiguous. So they added dyn as a necessary thing to write here to make clear that it's a trait object as opposed to a trait implementation of some sort, because it really is not. It was kind of special. This makes it less special. But the compiler will tell you. Yeah, now this works. So if we actually want to do this for num in make iterator, so let's use true here for now. Print that num. Okay, let's mark it. This is a 1. The other one is a 0. Okay. And now we go with false. And this is what in C++ you call virtual function calls. This is what Java does all the time with inheritance and things like that, and interfaces. This is what Go does with interfaces. This is what JavaScript, I think, also kind of does in its own way, but same idea. But the underlying thing is really, really close to virtual function calls, because you have some sort of indirection that then knows where to actually go, right? Because that's still kind of a switch there. Am I an array or am I this? Even though that actually, no, that's wrong. That isn't a switch, but you have to go through that additional pointer, let's say. You have to go through the box to make the call, and that's kind of the switch. Because that iterator here is now configured to know, I'm an array. So every call to it goes automatically to the array, but you have to go through it. So there is indirection in there, which makes these calls slower, right? They're not direct function calls anymore or method calls. They're now indirect ones, which is needed, but also gives you this benefit of not having to know exactly what it is. You can just work with it.
Right.
The other cost of it is you have an additional allocation. And also that is pretty costly, especially if it is in a tight loop. You feel that. I mean, really, Git Oxide is suffering from this. Not because Git Oxide is so wasteful, but when you decompress things with zlib, it does a lot of allocations for some reason. Like millions, literally millions. And that is, yeah, it's definitely visible. I mean, zlib is very, very slow compared to modern compressors and decompressors. And I guess that's one of the reasons that this is the case, really. Don't know. That must have been different times when allocation was cheaper than it is now or something like that. Okay.
And then, sorry, so the way you use it then, I mean, it's returning a box, but you're not really doing anything specific when using it, right? So it kind of unpacks it or dereferences it or like follows that pointer automatically.
Yes. Great point, by the way. Like this apparently implements into iterator automatically. Like this is a box now with an iterator inside, but it acts like an iterator. And is that automatic? No, it's not. Like somebody in the standard library implemented the standard library traits for boxes as well. Because when you do that with your own trait, my iterator, you will see that it totally doesn't behave like my iterator automatically. Like in certain situations where you need into iterator, you can't just use that, unfortunately.
Okay. So you are getting a box. It just knows how to handle standard calls to iterators, for example.
Yeah. And honestly, I'm a bit, I mean, maybe one day we will figure that out together, because I'm still a bit puzzled about like how this exactly works and whether I'm just, I mean, my basic understanding is if this is your own traits, you will have to implement your own trait, which is something you can do in your crate where you define that trait for the box with an item with an item that implements this. So you can But you have to hand implement this basically. So if you want people to box your trait and it should act naturally then you have to provide a blanket implementation. So for all the T's that implement my trait that are in a box, you can say that, do this. Basically just deref this thing and then call the actual trait that is behind that. Maybe there are better, nicer ways, but so far as far as I could tell, it's just manual work. Nothing is automatic, that's fair. So, but with the default traits, it's very usable and acts as you would expect, I'd say. Which also means that if we have something that is use iterator, where we say we want an iterator, we want to own it, where the item is U32. And this we could put in here, huh? Okay. Use it. Oop. Like this. Make iterator. So that should work. And I now just dropped some syntax here to actually try to see how that goes if the box is an actual iterator. This impl iterator is one way to write generics. It's the short form, so to say, the convenient form, the one I usually use when I just want to have something generic as a parameter. Quick and easy. And it does work. That's nice, as expected. But with your custom traits, definitely not. Out of the box.
Need to implement, yeah. Yeah, it's still a bit, not confusing, but definitely hidden away. I mean, even the way you write it, I mean, you say you're expecting an iterator here, but it's essentially just something that implements the iterator traits, and the box follows that rule, so it works.
Yes.
So you are working with a box, but it's kind of hidden away.
Yes, exactly. But it's also now compile time optimized, so to say. It still has that indirection that the box incurs, of course. But if you had a natural iterator here, like this, let's use one of these. Of course this works. And now this one, the second invocation, will be much faster than the first one. Yeah, because the additional indirection of the function call to next has been removed. At compile time. So that's also two different functions now, right? This is costing you twice in terms of space in the binary and so on. And this is what this kind of dynamic, monomorphism does. Like if you use impl or other forms of generics here, you might blow your file size, or you might increase your file size of the binary that you produce, but also you increase performance. But what about, can I just say, I want to use trait objects? Can I do that? Look at this. So now without the box, interestingly, huh? It does build. So that is valid syntax. What is this? What does that mean?
I'm just trying to think about that. So you're saying now the iter should be an actual trait object.
Yeah.
No, I'm not actually sure what that means. I mean, you're saying you want to own it, but then that thing is referenced and mutable. You need to explain that.
So fun thing, you can't really own it, right? It doesn't have a size known at compile time, you will see. And it tells you, put this in front. Put it behind a reference. And in this case, you want to change it because you have to iterate it. We have to call next, so it needs to be a mutable reference. This hides, this again is an indirection that you add here that makes trait objects usable directly. You can, I mean, I imagine it as what the box has inside, that's the trade object. Look at this here, right? And I want to borrow that mutably. So box, give me that thing mutably, and
Right.
I can use it directly. It's the thing on the heap. To do that, you don't have to know the compile size, or the size of the thing at compile time, which is beneficial. And that's another way, or that's the way you would write your function declarations if you don't want to create a new instance of a function depending on what kind of iterator goes in.
Yeah.
So in theory, we should be able to use the DIN iterator version as well with these. Let's see if we can. And you see that the compiler is able to create these trade objects on the fly. But that is special knowledge. It knows, I want a trade object. So now I give you this facade that gives you what you need to work with something that implements an iterator without you actually knowing what it really is. This also means one level of indirection as before. But we can use it naturally. So this returns a box, right? And if we dereference the box like this, it will provide us with one of these trade objects as well. Let's see if we can find the implementation here. Deref. Yeah. That doesn't help so much. Deref is implemented as another deref and another deref, and then then borrowing that. Yeah, I thought something like this would happen. So yeah, I don't know really how the box knows how to do that just by looking at this kind of code. Sorry, but it's probably all very logical.
Definitely.
So same thing. Oh wait, that's actually the wrong function. Oops. Should still work though. There you go. Okay. Okay, so now I think we went a little bit into trade object territory. What are trade objects? Even though we started out working with boxes a bit, because there's this one trait of boxes that I really want to highlight, which took me a while to understand. So how do I do this best? Yeah, so maybe just by doing something that is super not obvious. Oh, interesting that it does not allow that. Wait, it's the wrong position. Yeah, that's better. So still compiles. This plus static, you can add whenever you have, or let's say lifetime, you can add whenever you have trade objects or whenever you have these these generic declarations. Because you can say how you want them to be usable. Like, do they have to be static? Should they have some other lifetime associated with it? Static is that lifetime that says it's there for the duration of the program, / it's there for as long as this thing lives. Because that box has a lifetime, obviously. It lives on the stack somewhere, and as that goes out of scope, the box will be deallocated. So it doesn't ever live the entire duration of the program necessarily. But it doesn't mean that. It means it lives as long as you can see it here, and probably beyond that as well. Because it's owned. Like, you can imagine whatever is in the box is fully owned by that box, by that thing that is inside the box. And this is implied. So let's see. I have trouble making up an example where this is actually used, but I think I can. Ooh. Yes, let's make one up. Struct myvec, and then we just have an inner vector with u32s in it. So just some sort of hidden vector thingy that we declare an interface to. And then I want to be able to, I don't want to show them that I have a vector inside, but I want to provide an iterator to that thing, but only over borrowed items. I don't want to actually hand out ownership over that. I just want to borrow this out. So ideally the iterator that I return returns borrowed u32s, or to make it a bit more straightforward and we don't run into copy somehow, let's make this an own thing, string. Okay, now let's return an iterator. And we try to just say I hide everything, even though I know the type, there's only one thing, but for future changes, I want to hide this. So that that signature doesn't have to change anymore. Okay, now it gets interesting. Whenever you write an ampersand here or borrow something, your spidey senses have to trigger, because then oh,
you need a lifetime.
Something with lifetimes, probably. Is it automatic? Is it inferred stuff? Don't know. So let's just try to make it work here. If you return an iter, it should be the right thing. If you return it like this. Okay. Okay. Cool. This data with an anonymous lifetime is captured and required to live as long as static here. To declare that a trait object captures data from self-argument, you can add the lifetime here and the lifetime bound. Oh, that's nice. It actually tells you what to do. That's cool. That's the Rust compiler, because that kind of thing you would not ever guess. So the reason it tells you that is the default lifetime is this. So this is the same as writing that, right? Which means whatever is in here needs to be fully owned. But this is not fully owned, because now we have a borrow to something that is linked to the life of self, of that borrow here. So that's another borrow, which is the lifetime of myvec itself. And that's the problem. And if you write it like this, it's kind of more obvious that this is the problem. Like, how is that thing, with intern strings, by the way, that would work, because they have the static lifetime, something like that, right? So if I had string literals stored in that vector, that would work. Like, yeah, that iterator still doesn't have. So that might be better. What does it say? Oh, interesting. So interesting that the lifetime is still said to be, it's still not good enough. Because that, oh yeah, right, that iterator itself, it's not only the content of the iterator, but the iterator itself is bound to the lifetime of that vec. Because that's not an owning iterator, it's just an iterator that has a reference to inner. So now we have two borrows going on. We have the lifetime of this thing, which is static, so that's not a problem anymore. But that's not really the issue anyway, because the underlying issue is the lifetime of the vector itself, to that we have a reference to. And just declaring, declaring something that is statically or has a static lifetime like this helps you to kind of get closer to the issue, I guess, because then this won't be an issue anymore. Static is done. You're happy. It's as good as owning things because it just doesn't go away. It's always there. Rolling it back to this and back to this. We should be back to our original error, which kind of never changed. So now I do exactly as it says. I declare a, how does it call it again? It doesn't have, just an explicit lifetime bound. And this underscore, how does it look like to you, this one here?
Yeah, it's like a generic or kind of implied. I mean, you use that same syntax for variables, right? For example, in the match statement and stuff like that. It's basically something you don't really care about, but I'm guessing it can imply the lifetime here because it's only one.
Yes. So that's the inferred lifetime of whatever you need, so to say. And that's what you usually start with. If the compiler doesn't tell you, that's how I do it. I just say, okay, can you infer it in this location? Are you happy with this? So that you just specify, it's some other lifetime. It's not static anymore. Because now it implicitly kind of links these two up. That's the same then. But never add lifetimes just because you think they should be. Always let the compiler tell you. Because otherwise you might have too many lifetimes, and that also can be unhelpful. Okay, so that does work now. So now we have a box that returns something that is bound to the lifetime of something else. So yeah, what's inside of the box doesn't have a static lifetime anymore because it references something on the stack somewhere. And I think that's really important to understand, that by default, boxes expect to fully own their content. And some compiler errors, they are because of that. So if you ever have a box that just boxes stuff to get one of these trait objects, then you need to specify this. And just tell it what you borrow, essentially, so that you have the right lifetime associated with it. And that's that. And look, I can even say, oh, but this one has borrowed strings already. So I declare a lifetime that is passed in, that is from the outside, and these strings are held somewhere else. I borrow them with some lifetime, A, which is the lifetime of the thing inside. And now in order to make that work, well, I just pass these on, but apparently it's still not good enough. Is that better? Okay, interesting. A bit unexpected. Did I mess something up? Let's compile that to get the whole message. Yeah, right. It's a double borrow now. Okay, fair enough. Okay.
Oh.
Let's see if I can do copied and then be happy. Yes. So copied dissolves that. Read-only borrows can always be copied. We know that. Mutable borrows can only be moved. Makes sense. So that's a way to just keep it simple. And that works as well. But now we have two lifetimes. And I said don't add lifetimes unless you're told to. So let's be told to. Okay. See, it seems so logical to put this here, and I think it is still there. It's the right thing, but it doesn't need it. And if it doesn't need it, why put it? But this one here is still needed because we still borrow our inner vector implicitly by having an iterator pointing to it and iterating it. And that's boxes. And now I already said that these hide the size of the thing pointed to. And we can have functions like this, which use a borrowed iterator of that kind. So I wonder, because the size of the thing is clear at compile time, and I just want a facade to it, but it's still always owned here, right? Why would we have to put something on the heap for that? Because isn't this, yeah. I mean, this iterator, where does it live? Oh, okay, now I get it. Answering my own question. I was thinking, can't I do this? Can't I just give a borrowed dyn iterator somehow, because I have this here, right? Like, does this work? No. Because that iterator is also an object that we create. It is sized, and it can't be placed into a trait object.
Mm-hmm.
So trait objects, they can't ever hold their own data. They're only pointing at data in some way. They're referring to data. So this level of indirection. Whereas here, yeah, where does this iterator live? It can't live in that function, and we don't return it either. So we have to return something that keeps it alive, and that's the box.
Mm-hmm.
And this is why. There are situations when this is actually possible, like we did here, right? Look, here we have a temporary trait object because it's into iter that we call, and that thing lives on the stack. Like, this iterator is known to live somewhere, so we can just create a facade, a trait object to it, and put it into this, and give it to this function here. But here we have nothing to store that temporary, and that's the problem.
Mm-hmm.
Which also means that if you really wanted to do that, we could. Right? I should be able to. Like, there should just be some space. Like, if we put some space to hold that iterator, if you can put that space somewhere here and we use it on demand, then it should be possible. Just needs a storage location.
So just on the struct itself, yeah. Okay.
Yeah, should be possible. So it's only there when we actually create it. It's not there right away. Oh. Yeah, I already saw what this would mean. And no, it's not possible. Because now we have a self-referential struct. We would have an iterator that depends on, that is located in the same storage location, like on the same parent, as the thing that it points to. Mm-hmm. And now what happens if you move this? Like, this myvec can still be moved, but there's a reference inside of the iterator that just points to some memory location, right? Mm-hmm. And that memory location is currently movable because it's just living on a structure that moves at will. Every time we hand it over to somebody else, it moves, and then my borrowed thing, where does that point to? It points to the old location. And that is instant undefined behavior if you would try to use that. In C++, of course, you can do that. You can totally do that, but it doesn't help you. Here you cannot do that. But if you have some sort of storage location that might even be passed in or something, somebody else takes care of that, then it's all good. Then you can do this. But this is why boxes are, let's say, so useful, but you don't always need them. If you have storage for that thing, you don't need them. And sometimes I've seen, and I've used that myself, I've seen things like this. Yeah. So we want to have an iterator that depending on some condition is either one or the other. Something like that. So let's say our code always wants to be working with some iterator of something, but yeah, right now it's the same type even, so probably that doesn't matter so much. But as long as we have pre-allocated storage here, actually we don't even need to create that right now, we can probably return an iterator like that. So empty iter. Now we initialize it. So if this should be empty, whatever, based on some condition, we initialize this lazily and return an iterator to it. Otherwise, we use another one that is coming from somewhere else, like this. And you see now on demand, we have some storage that we fill in. We have this here, we fill it in on demand. And even though right now this is the same iterator type, so no boxing needed, no trait objects needed, this could as well be something that you have to abstract over by using trait objects. And then you might, I mean, as long as it's not an iterator, as long as something that has storage already, you should be able to just pass a borrow to it or make a trait object of it. That's not the perfect example. It just tries to show that, yes, you are able to even fill in or create objects on the fly based on some condition. And that's pretty, I think that's pretty widely unknown. Because that could be costly here, and you only incur that cost if needed. But then you can just, you know, gloss over different kinds of inputs that you only know or learn about at runtime, while, you know, having the same kind of thing to work with after. For item and iter, print line. Okay, so what's this? That should now be nothing, I guess. Maybe I give it a 2. If false, we see something else here for once. And there is our 2 here. So depending on my switch.
It works.
Yeah. And that's that. It's storage, it's trait objects, it's this pesky static lifetime that is implied for everything that is inside. But the compiler is helpful, as always. And I think that's all I know about boxes and trait objects and, you know, a little bit of generics we have here, but nothing big. Probably something for another session too, to make that a bit bigger. Yeah, that could be it. A few lines of code, but I think they do contain a lot of strange stuff. But I think to hammer it home, know about trait objects as a way to conform different types that otherwise you could hardly return, or you need some intermediate type for, like an enum that has both all the options that you could possibly return here, which might have benefits performance-wise, but of course you wouldn't want to do that just because. So that's usually the easier way of doing things. I think we also had a cast. Yeah.
Yeah, just quicker as well of writing, right? I mean, if you have to do the entire enum thing, implement everything yourself, this is just a dynamic, easy way to write this and conform different, or kind of the same types.
Yes. And in Rust, you totally avoid boxing things, like often, or I find myself doing that, or use this form a lot because I prefer performance over everything else. But that shouldn't be the default case. Like if this is code that doesn't, you know, that is somewhere high level, dealing with user input and whatnot, then just keep it easy, keep it simple, and boxes really help there. And trait objects. Yeah. I think that's mainly it. And I hope you learned something today, and everybody. So that's it for today, and thanks a lot for watching.
Thank you very much.
Bye-bye.